Hey everyone, this is Matthew Doyle. I did a session at GDC this year talking about procedural content creation and virtual reality and building virtual reality scenes inside of Autodesk's new game engine Stingray. For those of you that weren't able to make it to GDC to see the session, I thought I'd go ahead and record this video that you guys can check out and basically see just how easy it is to create virtual reality scenes inside of Stingray. But before we actually go into the details of how I did that, let me talk a little bit about what I think is important with virtual reality. So, first of all, let's define what the virtual reality experience is. Now, for me, that's 3 simple bullet points, and I kind of remember these 3 bullet points by a statement. And the statement is to draw them in physically and comfortably, talking about your users. You want to draw them into your world, you want to make them feel physically present, and you want them to be comfortable the whole time they're there. Now, so drawing them in, that's immersion. Making them feel like they're in the world physically, that's what we call presence. And then obviously comfortably, well, that would be comfort. Now, what is comfort exactly when it comes to virtual reality? Well, unlike non-virtual reality games, you've really got to be careful with things like motion sickness and excessive phobia usage and horror usage. If you're always trying to scare them with things that scare people in real life, like spiders or heights or anything like that, if you overuse that, that can make people very uncomfortable and they actually won't want to play the game any further. Motion sickness, that also can be a factor. Some of the newer virtual reality systems, the hardware claim to combat motion sickness pretty well, and part of the way they do that is by creating or keeping a high frame rate. And we'll talk a little bit more about what that means later in my presentation. But you still got to be careful with your emotions and the things you do in your world to try to avoid too much of that feeling. And that's really only going to affect a certain subset of people. There are a lot of people out there who don't get motion sick with VR, but there are enough of them that you do still have to be mindful of that. And other things like neck strain. I mean, keep in mind that the average person in real life, when they're walking around in the world, they don't turn their heads 90 degrees plus constantly. They're not looking behind themselves all the time. They're generally going to only look in a certain field of view, maybe about a 45 degrees off of center, so 90 degrees total on average, I would say, field of view. You don't want to have your virtual world where you're constantly expecting your players to look far left, far right, and so forth. So which is kind of strange, because when you think about it, if they're not really going to be looking that much around, how different is it from really just looking at a monitor? Well, it's still enough different that your players will notice it. But still, just be careful about making them look too much in other directions to cause repeated neck strain and such. So let's ask the question how VR can succeed. Obviously, 2016 has been called the year of VR by a lot in the press. And there's a lot of hype around VR right now. And VR has been around since the 70s at least, in some form or another. And if you really go far back enough to the late 1800s even, you could say VR has existed, because they had these view screen little contraptions where it showed images. And so you could kind of call that virtual reality, where people were able to see a world that they didn't normally look at through a viewfinder. But the reality is the VR these days is a lot more impressive than it was, obviously, back in the 70s and 80s. The headsets are smaller. You have a lot less latency, which causes the frame rate to be better, and the responsiveness from the game to the images that the player is seeing are a lot better with latency. So, what are some things that we can do to help VR to succeed? Well, some things are controlled by the hardware vendors. And that includes cost of hardware. Obviously, right now, the costs are kind of high because making VR systems is pretty expensive. And so right now, you may only have mostly the early adopters that are buying the hardware. But even so, they're still selling out. All the VR headsets are selling out right now, which is really impressive. And then also another thing controlled by hardware vendors is, to a certain degree, is comfort. And that is physical comfort. Obviously, right now, all VR headsets are tethered. They're wired, which means you have to stay close to your computer, and you can't spin around 360 degrees without getting wrapped up in cables. So I think maybe wireless VR is the future for sure. I'd definitely like to see that myself. But it also, comfort means a smaller headset, better lenses for the eyes so they don't fog up so much, straps, how it stays on your head, and so forth. Those are all things controlled by the hardware guys. Also controls. I don't know if we've really solved walking in virtual reality yet properly. We do have hand controls that can be used and game pads that can be used, as well as keyboard and mouse. We also have what's called a gaze controlled VR game, where it's basically just controlled by where the player looks. Where he looks is where the character goes, or where the character shoots, and so forth. But I would really like to see walking in VR solved in a better way, a more intuitive way. Obviously, most people don't want a giant treadmill in their house, in front of their TV for virtual experiences. So there's got to be something, and hopefully they will solve this problem eventually. And also quality. Quality is primarily controlled by the hardware vendors. Obviously, that includes resolution of the screens that are used for viewing, as well as the latency I talked about, among other things. So these are things that as game developers, we don't really have a lot of control over, and we've just got to basically have faith that the hardware vendors are going to ultimately solve some of these issues. However, as game developers, we do have some control over how VR can succeed, and that is primarily by us creating killer apps. And a killer app to me is basically something that's obviously beautiful, highly performant in virtual reality, and you'll understand why as I talk a little bit more about VSync and frame rate, as well as creating an intriguing and engaging environment, all the things that you would expect to do for a non-VR game. We've already got some really, if you look back over the history of games, really impressive, beautiful environments and worlds. Obviously, with each next generation of console and each year that passes for PC games, they just get better and better looking. It sometimes boggles my mind how good things are starting to look, and I begin to wonder, are we going to hit a ceiling here as far as man hours required to build this stuff and the amount of time it takes to build a game, to make it look ultimately, so realistic that you couldn't tell the difference. But the point is, we also need to think about these things when we're creating VR apps. We need to create these beautiful environments that are fun to be in, that are engaging, but they also are actually requiring a lot more performance than your standard game on a console or PC, and that's due to a higher frame rate, which we're going to talk about a little bit later. But just briefly, virtual reality requires a much higher frame rate in order for it to look smooth and also to combat motion sickness. So let's go ahead and get into Stingray now. I'm going to actually show you guys how to use Stingray to build virtual reality. And before we do, I'll just mention that Stingray, Autodesk Game Engine, currently supports the Oculus as well as the HTC Vive VR systems. And with Oculus, as of this video, we support, Autodesk supports 0.8. And I believe, obviously 1.0, which is the consumer release of Oculus, is already in the pipe to be supported as well. So I'm using Oculus Dev Kit 2 for this demonstration, and it's using 0.8 SDK. Now, obviously, if you want to build scenes in Stingray for virtual reality, you're going to need the proper SDK. 0.8 runtime is all you really need. And you'll also need DirectX SDK installed on your computer as well. And then, of course, the version of Stingray that I'm using, which is 1.2, which was released at GDC. And yeah, that's about it. So let's go ahead and get started. Okay, inside of Stingray, we're in the project manager here. And we're going to go ahead and create a new virtual reality project from a template here. So if you go to the Templates tab, there you'll see we've got several templates that you can create from. We have the basic template, a character-based template, vehicle physics template, and then right here we have a VR template. So we're going to go ahead and select that, and we'll just choose create, and we just need to pick our folder where we want this to live. So I'm going to jump into my usual Stingray projects folder here, and we'll just call this VR GDC. All right, and we're going to call the name of this project VR GDC as well. We can put a description and whatnot. We'll just go ahead and hit create. Okay, so here we are inside of our newly created VR template project. This is obviously for an Oculus. And what we're going to do is we're going to show you how to build a roller coaster VR demo today. Now, the roller coaster itself was created using 3D Studio Max's Max Creation Graph, so it's completely procedural. And it's really cool because it's basically just built on a spline. So all you have to do is create a spline loop of any shape with loops and twists and turns, and the MCG will automatically create the roller coaster for you, which is super cool because once you've brought it into Stingray, if you need to make changes to the roller coaster, maybe you don't like a vista shot, maybe you want to move something, tweak something, all you got to do is go back into Max, move that spline a little bit, re-export the roller coaster, and you're good to go. But I don't really have time during my presentation to show you how to do something with Max Creation Graph, but I do want to go ahead and import our roller coaster. And so inside of my project here, I've got a roller coaster folder. We're going to go ahead and hit import. So here are the source assets for my roller coaster. And here's my original file, coaster rails. This is an FBX file. So this is just going to be a mesh with materials. So we're going to go ahead and turn off cameras, and we don't need animations, and we'll go ahead and port that into our project. All right, so you can see here that Stingray brought in all of the files associated with this roller coaster. These files here, these are all our materials. These are shader effects materials. If you're not familiar with shader effects, that's the real-time GPU-based shader tool, and it carries over and transfers between 3ds Max, Maya, Maya LT, as well as Stingray. So you build your shader once, and it's built for all time. You don't have to go back and rebuild it for Stingray. So here's our actual roller coaster mesh. We're just going to drop it into the level here. And we just want to make sure it's centered at the origin of our world. So we'll go in here to the properties panel, make sure it's all zeroed out. Okay. Let's go ahead and turn the grid off here so we can see our roller coaster. All this again created using a spline. And then the Max Creation Graph did all the magic and created the actual track, and as well as all the rivets and the poles and everything. Very, very cool. All right, so next thing we need to do is actually import the camera. So the other thing the Max Creation Graph did was create a camera that's animated along the path of the roller coaster. So let's go ahead and do a quick import of that. And here it is, coaster camera. Now in this case, we want to import the camera and we want animations as well. All right, and we're going to go ahead and create an animation folder, and we'll hit import. All right, so this is our camera, coaster camera B. You can see here we have a cart as well. So what I'm going to do is I'm going to just open that up for a second inside of the unit editor. And in order to prepare this for use inside of our demo, we need to do one thing. We need to add a physics actor to this. Now the physics actor is going to allow us to have collision. And the reason why we need collision on our coaster is if we have any triggers in the level for any events to happen or whatnot, we need to have that physics actor. So what we're going to do is we're just going to select the actual cart mesh, and we'll go to create physics actor. There's our physics actor cart, and let's just go ahead and go over to the properties panel here and make some adjustments. We're going to set the node to cart. We're going to set the template to keyframed because this is going to be a keyframed animated cart. We don't have to worry about changing the mass or anything like that. We'll leave mesh as cart, and type, we're just going to set that to box. That's good enough for our purposes there. All right, so that's done. We'll go ahead and save this unit. Okay, so we're going to go into the animation folder, and we'll go ahead and load the actual animation just so you can get a preview of how this looks. So go ahead and hit play. And we can see here that the cart is animating along the path of the roller coaster. Now, what's happening is the cart is basically animated around 0, 0, 0, or the origin of the world. And so because of that, because of the way we brought this in, we're going to have to do some special things to have 3D positional audio, because otherwise the audio would only be relative to the origin of the world. So we're going to have to create a proxy player or listener that follows the cart. And I'll show you how to do that in a little bit. But let's go ahead and move on. So to get our cart into the world, we'll just go back over here and we'll drag the cart into the world. We'll go over to the property panel and we're going to zero it out as well. All right. So now if we zoom in on the cart, it should be properly positioned there, right on the roller coaster, ready to go. All right, so now let's go ahead and set up some flow. Now flow is Stingray's visual scripting tool that allows artists and whatnot, people who aren't engineers, to be able to add gameplay logic and other things like that to their games. And you could literally create a fully playable game just using Flow. But for the case of our demo, we're just going to have some basic controls and things like that we're going to add in here because it's actually pretty simple. So let's go over to the Flow tab here. All right, so the first thing we want to do is we want to set our active camera. So in order to do that, we need to make sure we have our camera selected here in the Explorer. I'm going to right click and choose Create Level Unit Coaster Camera B. So now what I want to do is I want to get the actual camera unit or the actual camera off of this unit. So we'll just come over here and we'll go to Unit, Get Unit Camera. There we go. Now we're going to actually use this camera to set it as the active camera. So we'll drag off of the camera here and we'll choose Camera, Set Active Camera. We're going to tie the unit back to this unit here. And finally, we need to do this when the level starts. So we'll pull off of the in and we'll choose Event, Level Loaded. Okay, so one more thing I want to do here is to actually tie some input from a device like a gamepad or whatever to actually start the animation of the roller coaster. So what we're going to do is we're going to right click and choose Input. And in this case, I'm going to use an Xbox controller. So we'll do Xbox button. And for the button itself, we'll click on Name here. We're going to go with the Start button. All right, and once pressed, we want to play an animation. So we'll just pull this over here and choose Animation, Animation, Clip, Reset, and Play. All right, so the animation that we're going to play is going to be pulled from a unit. And in this case, it's our camera unit, the roller coaster cart itself. And then we can click on Animation here to get the name of the animation. And that animation here, Coaster Camera B. We don't want it to loop, so we're going to change that to false. All right, and that should be our basic setup for controlling the start of the roller coaster. So if we jump back over, and let's just go ahead and save what we've got. So we'll save this in our Levels folder. And let's just go ahead and do a quick test. We're going to just play the level itself. All right, so at this point, we're not actually working in virtual reality. Just FYI, this is just playing the level itself, and it's just going to play like in a regular gameplay window. Now, if I press Start, we can see that the roller coaster is moving, the camera is moving, and the cart is actually there, but we're clipping. Our near clipping is actually really short, so you can't actually see. That's why you can see part of the roller coaster track is clipping there. But we'll talk about clipping planes a little bit later, and we'll solve that issue. But so far, so good. We've got our cart imported, we've got our animation, and we can actually control it with the game controller. All right, so let's look at what it actually takes to get this working inside of your Oculus headset. And it's a lot easier than you might think, thanks to the template. Everything's pretty much already set up for you. So if you look in your asset browser and scroll to the bottom, you're going to find a script folder, and inside that a Lua folder. And in here you're going to find all of your Lua scripts. The two important ones here are the ones that say Oculus, Oculus Input Mapper, and Oculus VR. I'm not going to actually open these up and go into detail on what's in them, but basically these two script files will allow the game to communicate with the Oculus SDK. So those are pretty important, and feel free to dig through them, but they're very basic files. They're not too hard to understand. But what we want to look at today to actually get our demo working is the project file. So we're going to open project.lua in our script editor. Now the first thing we need to do is we need to actually add our project level inside the project.level names table here. All right, and so what we're going to do is we're going to say GDC_VR, which is the name of our level, equals content/levels/GDC_VR, and that's basically the path to that level. So that's the first step. We now have that level in there, so we can actually call upon it. Now if you scroll down just a little bit here, you're going to find where the Oculus VR system and Oculus Input Mapper are initialized as new tables inside of Lua, and that basically enables them. And then just below that, you've got all of these settings here for the Oculus, things like the IPD or interpupillary distance, which can be set here in the program. Now, I know the new Oculus consumer model is supposed to have a physical IPD adjustment as well, but if you want the player to be able to adjust these with a slider or something in a menu, you can certainly do that, as well as player height, eye height, and some of the other things that you can set. But we don't need to worry about that for our demonstration. We're just going to go ahead and scroll down a little bit further. And in order to get our VR level running, we need to specify it here where it says standalone init level name. We're going to change this from the menu, so project.levelnames.menu. We're going to change that to our GDC VR level. Okay. Now, one other thing I'd like to call your attention to, if you go down to project.onInitComplete, and inside of here, this is where the Oculus VR system is initialized. And when it gets initialized, it specifies the near and far clipping planes for the Oculus headset. Now, the near and far clipping plane here is actually different from the near and far clipping plane for the viewport, as well as the normal camera in a Stingray gameplay window. So you need to set the Oculus clipping planes here. Now, these are in meters. So we have 1,000 meters is the far clipping plane. And the near clipping plane is at 0.01 meters, or 1/100th of a meter. Now, keep in mind that these values will affect your frame rate with the headset, obviously. So you want to be very careful to make sure that you don't set your far clipping plane too far, and you don't set your near clipping plane to be too small, too granular. Now, if you have a game where you have like lots of indoor tunnel-y type stuff, you can obviously set your clipping plane pretty low, and that's going to help your performance. In the case of our roller coaster demo, I went ahead and stayed with 1,000 meters, which is the default setting here. But in the case of the near clipping plane, I'm going to go ahead and change this to 0.1. And the reason being is at 0.01, we're basically we're going to have a lot of Z fighting when we're looking at things that are far away. Because the depth buffer is basically, the accuracy of the depth buffer is too great. So by setting it a little bit less granular, by increasing this value, we're going to help combat the Z fighting. Okay, so that's just some basic setup there. That's all we really need to do to get this working in virtual reality. So let's go ahead and save this file and jump back over, and we can actually run the project now. And there we go. We have everything in virtual reality. So I can move the headset around. We can see the cart. Our roller coaster is there. If I hit start, we start to move. So just like that. Very easy to set up. All right, so let's actually jump over to doing a little more detailed work here on our roller coaster. We're going to talk about actually setting up 3D audio. So that, obviously 3D audio is a pretty important part of the virtual experience, especially to help them feel more present in the environment. And a lot of times players are going to be using headphones for that. And so obviously they're going to be able to hear whether the audio is coming from the left or the right or above and whatnot. And so I'm going to show you how to set that up inside of Stingray now. All right, so in order for us to have 3D audio, if you remember when we imported the roller coaster, you can see here when I select it that the roller coaster, its position is at the origin of the world, or 0, 0, 0, and it's always there no matter where this coaster moves to. And that's because of the way we created it and imported it. It's actually an animation, and animation centered around the origin rather than the coaster just following something else. That's how we set it up. So in order to combat the fact that the coaster is at 0, 0, 0, if we want 3D audio, we have to basically create a proxy unit here, or a player, that will follow the roller coaster and allow us to tell the Wise Audio listener to follow it. So Stingray comes with Wise. If you're not familiar with it, it's a great audio SDK used in a lot of games. And we can actually tie into Wise using the flow inside of Stingray, the visual scripting tool. So let's start out by setting up our player proxy inside of the roller coaster. Now to do that, I'm just going to create a sphere object here to represent our player. You could actually have a player mesh in here, which might be a lot better for the sense of presence and making the player feel like they're actually there, to be able to look down and see their legs and stuff. But I'm just going to use a sphere object for now. And what we can do is we can make this sphere object really small. We can hide it. Let's just bring the scale down over here to like 0.25. We could even put a material on it that makes it transparent. In this case, I'm just going to kind of move it. All right, so I'm just going to move it there inside of the coaster, and we'll go ahead and jump over to level flow now. Let's actually go ahead and name this sphere primitive something a little more descriptive. We'll call it player proxy. All right, so first up, we're going to go ahead and bring our player proxy into flow here. So we'll right click and choose create level unit player proxy. Again, we had to make sure we had player proxy selected. Okay, so next up, remember we created a physics actor on our roller coaster, and we need to bring that inside of flow as well, because what we're going to do is we're going to basically move our player proxy based on that physics actor, because that physics actor is going to actually move and have a different value, a different position value as it moves through the level, while the roller coaster itself does not. So in order to get the physics actor, we're just going to go ahead and pull it off of our roller coaster unit here, and we'll go down to unit, get unit actor. Okay, and this gives us access to that physics actor. So now we want to get the actor's position. So we'll just pull off of actor, and we'll go physics actor, and then get actor position, just like that. Now once we have the position, we need to set this unit to match the same position. So to do that, we're going to use a node called set unit local position. So we'll just pull off of unit here, and we'll choose unit, set unit local position. Okay, and the position we're going to set it to is, you guessed it, the position of the actor. All right, and what we want to do is we want to do this on every game loop or every level update. So we'll pull off the in here, and we'll go to event, level update. Okay, so now that we've got our player proxy following the roller coaster, remember the point of this is to be able to have 3D positional audio. Now to get that effect, we need to tell Wise's audio listener to move with the player proxy as well. So we'll go ahead and pull off of the out value here, and what we're going to do is we're going to go under audio, Wise, global, and we're going to choose move or Wise move listener to unit. Now unfortunately, it would be great if we could have just tied this listener to the actor of our cart, but that is not an option. We have to tie it to a unit. And that's why we have our player proxy unit, which is being moved to the physics actor of our cart. Okay, so we're going to go ahead and tie the unit right back to our player unit here. And that's it. We're all set. We've got our 3D positional audio listener following our player proxy, so that now as it moves through, as the roller coaster moves through the level, anytime it passes an audio source, it will detect it and play that sound in the proper speaker of the headphones or speaker system. All right, and let's go ahead and group this for organization. So we'll just select all of this, and we'll right click on one of these nodes here and choose group, and then we can just double click this to name it, and we'll call this set audio listener location. All right. Okay, so let's actually load up Wise and look at how easy it is to create 3D positional audio for our demo here. And when you create your projects in Stingray, they're automatically going to create a Wise project for you. And so if we click on the audio folder here in the asset browser, we can see we've already got a sound bank. And a sound bank is basically just a way to organize audio files for your project. You can create multiple sound banks for any project. And in this case, we're just going to use the default sound bank. In fact, here we have this in our default sound bank. We have one sound already. That's the spawn sound. That's what you hear when you start up a default level. So what we're going to do is we're going to just add one audio file here, one positional audio file that we can use for our roller coaster. So we'll double click the default sound bank, and that's going to load up the Wise audio editing tool for us. Okay, so here we are inside of the Wise audio editing tool. Comes with Stingray. And Wise is a very powerful SDK, and the tool itself is something that you could spend a couple of hours talking about how to use. My intention in this demonstration is not to teach you how to use Wise, but I will show you very briefly how to go ahead and add an audio file and set it up for 3D positional audio. So inside of Wise, we have our audio tab here. If we open this actor mixer hierarchy where it says default work unit, we'll see we have categories here: music, sound effects, and VO. Sound effects has that default sound effects spawn sound. We want to add a new sound here, so I'm just going to right click on sound effects and choose import audio files. So we'll go ahead and browse to the files that we need. Okay, so let's go ahead and add, we're going to add this lava loop. It's kind of a nice bubbling lava sound here. Okay, so we've got our lava loop. Now if we go ahead and click on lava loop, we can see over here in the middle all of the options that we have for this sound. We can adjust the volume, the pitch. We've got low pass and high pass filters here. We can make it a looping sound. We're going to go ahead and do that. We'll turn on looping. But what we want to do here for 3D positional audio is we're going to click on positioning, and then we're going to click override parent, and in the drop down here we're going to set it to 3D. So here in the attenuation area, we're going to create a new attenuation. We'll just call this lava. And if we edit the attenuation, we can see that we have a very basic linear attenuation here. And the distance for the max attenuation is 100 meters. So we'll just go ahead and leave that at 100 meters, but obviously I could change this to 5 meters, 500 meters, whatever I want. And of course I can adjust the curve. I can actually make changes to how the curve looks here, but we're going to just leave it a linear attenuation. Now at 0, that's obviously the origin. That's going to be maximum volume, and at 100, once you go past that, you're not going to hear it anymore. And of course it's going to drop down as it goes. All right, so we're just going to go ahead and close that, and we'll go ahead and save what we've got so far. Now, in order to make use of this inside of our project, we need to create a new event based on this sound. So I'm going to right click my lava loop, and I'm going to choose new event, play. All right, and this creates our new event. I'm going to rename it to SFX _ lava. Okay, if I play it, you can hear the lava playing. All right. Now we're going to jump over to the Events tab, and we're just going to open up our default work unit here. So we just want to make sure this SFX Lava is grouped under Sound Effects, and we'll just do a quick save as well. Okay. So now we have our event. We just need to go ahead and do one last thing, and that's to publish our sound bank to the project. So if we go to Layouts and then Sound Bank, that's going to bring up the sound bank layout here. And we'll just go ahead and open up our default work unit and make sure that default is checked. In this case, we're just going to set it up for Windows for our platforms, and then English for our language, and we'll hit generate. Okay, so now we can jump back over to our Stingray project, and we see here our lava sound effects is added to the project. So how do we actually make use of this lava sound effect now that it's in? Well, that's pretty easy. We just need to go ahead and add an audio source to our level. So under Create, we're going to go to Helpers, and we'll scroll down to find Audio Source. All right, and we'll just go ahead and add our audio source right here on the roller coaster itself. Okay, and we'll call this audio source Lava Source. All right, so next thing we need to do is specify which sound bank that this audio source uses. So we'll go into the properties here under Wise Properties. And we'll choose the default sound bank. And we also need to specify the event. We created that event inside of Wise. If you recall, it was SFX Lava. So we'll select that. All right, so once we've selected the actual event, you can see that it visualizes a sphere here. And this is the attenuation sphere of our lava audio sound. And that's 100 meters. Now this is based off of a point. So basically the very center of our audio source, an infinitesimally small point, is the source of our audio. But we can change this to a sphere. And by changing it to a sphere, you can see here that we have the max attenuation is anything within the blue sphere, and of course the limit of our attenuation is outside of our green sphere. So I'm just going to leave it set to sphere, and all we need to do now is move it into position. So if I drag this guy over here to the left a little bit, we can see it's currently the cart is not in it, so we shouldn't hear it when it starts. but as the cart moves up the roller coaster path, we should start to hear that sound off to the left. So let's go ahead and do a quick test. We'll save the level, and we'll just play the level itself. All right, so we can't hear any lava right now. Let's go ahead and hit the start button to get the coaster moving. And there we go. We can hear the lava coming from the left. Perfect. Okay, so that's pretty much it for the actual demonstration of how to build all this. Let's actually load the final version of this and talk a little bit about optimizing levels for VR and polishing them. So I'm going to jump back over to the project manager, and we'll go ahead and load this final version of our roller coaster demo here. Okay, so before we actually finish up inside of Stingray, let's look at another slide here real quick and talk a little bit about some of the things that we want to accomplish here to optimize and polish our VR content in Stingray. So I talked a little bit earlier about frame rate and latency and all of that and motion sickness. And the thing is in virtual reality, you have to have higher frame rates. For one thing, it combats motion sickness, but for another thing, it just looks a lot smoother, a lot more realistic, and avoids things like ghosting and stuttering, which are all things that can pull your player out of the world and jar them from the experience. So with the Oculus Dev Kit 2, those run at 75 Hertz or 75 frames per second. Now, Oculus consumer model and the HTC Vive both run at 90 Hertz or 90 frames per second. So the thing about running at a higher frame rate is it also tends to mean that the quality of the graphics are going to have to be adjusted. I don't think we're quite there yet to the day where you can have super realistic, say, The Order or Assassin's Creed Syndicate or Tom Clancy's Division quality graphics in virtual reality quite yet because of the demands of frame rate. Because even at 75 Hertz, you need to render every frame in about 13 milliseconds or less. And anything above that is going to start to cause ghosting or stuttering. You always need to maintain VSync with the headset. And then, of course, with the consumer models in HTC Vive, the constraints are even greater. At 90 Hertz, you have to render everything at 11 milliseconds or less. Everything has game loop, everything has to be done at 11 milliseconds or less. And if you don't, like I said, you're going to see ghosting, stuttering, and you may even induce motion sickness because of this. So bear in mind that it's very important to optimize your VR content to maintain the proper frame rate or VSync with your headset. Some other things we can do is lighting. We need to look into how we can optimize our lighting. Now, obviously, real-time dynamic shadows and global illumination are beautiful, but for VR, I don't think that the technology is quite there yet. So most of the time, you're going to want to bake your lighting. And I'll show you just briefly how you bake your lighting inside of Stingray. Some things we can also do is optimize our shading environment, and that includes things like screen space reflections, light bloom, as well as screen space ambient occlusion, all of those types of effects, blurring, depth of field, motion blur, all of those things can be adjusted. And you basically want to adjust them based upon whether or not your content is running at VSync. And if it's able to run at VSync with some of these things enabled, then you can keep them on, obviously. But if not, you're going to have to consider shutting some of these things off. And we'll look at the settings INI file for a few things that we can do to tweak this. And then finally, you're going to want to have LODs for all your models. Obviously, if you have a very high model count in your world with a lot of polygons to each model, you're going to want to have LODs so that those models are reduced as they're further away from the camera, and obviously that helps to improve your frame rate. So, but let's actually look at in Stingray how you would do some of this stuff now. Okay, so before we look at some of the optimization tricks, let's look at some of the things we can do with shader effects inside of Stingray. So for instance here, if we wanted to improve this water a little bit, and the water looks pretty nice for our level here is more of a cartoony look to it, and the water is already pretty good. We've got a nice animated normal map on it, and it's transparent, and it's got some specularity, but maybe we want to add actual refraction to it. Well, that's easy enough with shader effects. Let's go ahead and select the water, and in the properties panel here, we're going to go to the material here and click this little arrow, and that will bring us to the actual water material here. And in the properties panel here, we can actually see all of our sliders and whatnot for controlling this shader. And this is a physically based shader, so we can see we have roughness and metallicness and so forth. And all these sliders can be adjusted to change these values. But what we want to do is we want to actually alter the shader graph so that we add some refraction to it. So we're going to open the shader graph here. Okay, so here we have the actual shader graph. I'm going to make this bigger so you can see it. Okay, so this is obviously a node-based shader creation tool. And again, this is all stuff that runs on the GPU. So what we're going to do is we're just going to come over here and we're going to add some nodes here so that we get some refraction. You can see here that this physically based shader already has a refraction input. And we just need to tell that input how we want it to behave, where it gets all of its information to be able to show the refraction. And what we're going to do is we're just going to use the normal map that's already here, which is nicely animated using some panners, and we're just going to tie that into the refraction as well. So to do that, we want to basically just multiply this normal map by a scalar value and then tie that straight into refraction. So very easy. So we're just going to right click here and choose add. We're going to go constant scalar. All right, and that's going to be our scalar here. And we're going to click on the pencil here and we're just going to put in a value of 100. Okay. Now we're going to go ahead and add the multiply. So we'll right click again and we'll go to math and multiply. So we're going to multiply our scalar by the RGB alpha of our normal map, and then we're going to tie that straight into refraction. Okay, we'll go ahead and close this window down, and that should be it. So if we save that, you can already see some refraction in the viewport here. So let me see if I can get a good view here for you. Let's go ahead and zoom in on this rock. And there you go. You can see the refraction as the normal map ripples over it. Let's wait for a second. You can see it there. It's a subtle effect, but it looks really good. So that's just one way to add some cool polish to your levels, and that's using physically based shaders inside of Stingray and making some really cool looks and effects using the Stingray Shader Effects tool is actually very easy, as you can see there. In fact, we've got another shader over here on the volcano, the lava itself. We zoom in a little bit here, you can see. So here's another pretty cool shader, and this was also done using Shader Effects Graph. Once again, we have a panner, so we're animating the texture over that surface. All right. So we talked about the importance of VSync and maintaining a good frame rate. And one way that you can determine what kind of frame rate you're going to be getting is using the performance visualizing tools inside of Stingray here. So if we go to the viewport, we click on view here, we have the performance HUD, and we can turn on FPS here. And this tells us what our FPS is inside the viewport. And in this case, we're pretty much hitting 60 frames a second. And now bear in mind the viewport is locked to 60 frames a second maximum. And so even if you're getting more than 60 frames a second, you're not going to see that number go up any higher. Whereas when Stingray pipes out the images to the Oculus, they're going to be locked, in the case of DevKit 2, to 75 hertz, and the consumer version would be 90 hertz or 90 frames per second. Now, if you want to use the performance HUD in something other than the viewport, you can come down to the command line way down at the bottom here, and we can actually change this drop down here from editor engine to whatever executable is running the Stingray VR demo, and then just simply type perf HUD FPS or perf HUD artist. Now, if we turn off the FPS view, we can turn on the artist view, and this is going to give us a lot more detail on the amount of memory our demo is taking up on the video card, as well as FPS, but also things like how much time the G buffer is taking, how much time global lighting is taking, emissives are taking, transparency, everything. And then of course at the bottom here we have the total amount of time per frame, and we can see here that this is hitting it's roughly 11 milliseconds, I think, and every once in a while it spikes a up to roughly 15 milliseconds. So here's a good way of looking and finding out what in your scene may be causing slowdown. So you can see here as I'm rotating around, the G buffer is really kind of spiking pretty high. And that's because there are a lot of objects in this scene, and the poly count is not super high, but obviously high enough to cause a spike when we really zoom out here and rotate around. So we could see here, maybe if I wanted to make some tweaks, I would make tweaks to the actual geometry itself. I would create some LODs for my objects so that they show less detailed versions as I'm further away. I could maybe reduce some of the amount of objects I have, or even combine objects into one object, and that would help with my G buffer, bringing that down some. Okay, so let's go ahead and turn that off, and let's talk about lighting for a second. Now, as I said, you're not going to generally want to have real-time lighting for virtual reality yet. You're generally going to want to bake your lighting, and that's done very easily from the Bake Light Maps tab here. Now, inside Stingray, there are two ways to bake light maps. You can use Beast, which is a tried and true global illumination light map baking tool. It creates very realistic light maps that take into account light color bleed and whatnot, and the way light actually behaves in the real world. And that's fairly fast to bake the lighting. And you have, when you choose Beast, you have a lot of settings and options that you can manually come in and specify. Or you could use the new Beta Light Map Baker. It's currently just called Stingray Beta. And you don't have a lot of options here. Specifically, you simply have the ability to specify the texel scale of your light map, and that, of course, has to do with how detailed it looks, but also the number of passes it takes to create the light map. And finally, the skylight intensity, how bright you want the skylight to be. And you just hit bake, and that's pretty much it to baking your light maps. Now, if you bake your light maps with Beast, you're not going to have access to them. They're compiled immediately into the data folder. But if you bake your light maps using the new Stingray Beta GPU-based light map baker, I might add, it will give you access to those light maps in a folder, in the level folder. So you can actually go in and modify the light maps if you need to in an image editing tool. All right, so that's one way definitely to improve your performance. You're going to see a huge performance hit on your frame rate if you use real-time lighting and shadows. So keep that in mind. So if we jump over to our shading environment, so we'll go to the Explorer tab and click on our default shading environment. This is created with the project when you first build a level, when you build any levels. We can see here in the shading environment we have things like global lighting, cascading shadow maps, fog, exposure, screen space ambient occlusion, reflections, depth of field, bloom, etc., etc., etc. These are all great things to make your levels look really super cool. And in this case, I have fog enabled. So obviously, if I turn off my fog here, you can see the difference. And then I also have light bloom enabled. So we'll go to light bloom here. You can see the difference, obviously, when I turn that on and off. Now, these are the only two that I am using. This is what I found I got the best performance for my demo with. And what you're going to need to do is go through these and basically turn them on one at a time and see what kind of performance hit you take in VR, in your Oculus. And if it still runs great and you don't have any ghosting problems or stuttering, then by all means, if you want to use these screen space effects, feel free to use them. Otherwise, you're really just going to have to be careful because, if I were to turn all these on, it gets really expensive and it's going to have a huge impact on the frame rate. And just keep in mind, you've got to maintain that VSync in VR. It's really important. Any stuttering or ghosting will really have a bigger impact on your player because of just the way VR affects the brain is a little bit different than just looking at a monitor. Okay, that covers the shading environment. Now, with the shading environment, we also have a settings file that will specifically also enable or disable these things for virtual reality. So if we jump over to our VR project folder in the asset browser, and we open settings.ini in our script editor, this is basically the project file that specifies things like the name of the window for the executable, the default resolution, things like that. But it also has under render settings the VR setup. So here we have our Oculus DK2 setup. We've got our eye resolution and whatnot. Now, the things I want to point out here for optimization are VR target scale, and then below that, all these post effects. Now, in line with our shading environment where we can specify fog and light bloom and whatnot, you're also going to find some of these post effects in here. And we can enable or disable them here as well. So you're going to want to make sure that this matches your shading environment. So here we can see I've got full screen anti-aliasing disabled. I've got temporal anti-aliasing disabled, ambient occlusion, but I do have light bloom. And then of course I've disabled screen space reflections and lens quality. Again, you really want to test these. If you want something like lens quality or screen space reflections, turn them on here, turn them on in your shading environment, and then test and see what kind of a frame rate you're getting, and one at a time, and then enable and disable them until you get exactly what you want while still maintaining your frame rate. It's very important. Okay, and then last of all, this VR target scale here. This is going to basically enable or disable super sampling, which helps to reduce aliasing artifacts. Now this is defaulted, I believe, at 1.2, and for my project I've set it at 1.0. 1.0 basically disables it, so the scene is a little more aliased. You can see the stair step on the edges of objects and whatnot. Whereas with a higher rate value here, it would help to blend that aliasing effect on the edges of your objects. It would look smoother. You can try it with that, and if you don't have a performance hit, then by all means keep the super sampling enabled. But if you do, you can always drop this down to 1.0, which basically turns it off. Okay. All right. So that's pretty much going to cover it for some optimization tricks for your VR and polishing. Basically, keep in mind that keeping that high frame rate is very, very important. I know with PC and console games, there are plenty of 30 hertz games that look great and play great. Most games out are actually 30 frames a second. Usually your 60 frames per second games are your going to be shooters and racing games and things like that, and fighting games. But the rest of the games out there are generally 30 frames per second, and they run great. But when it comes to VR, you really have to have a higher frame rate. You have to have that 90 hertz, 90 frames a second. That means, obviously, you're going to have to sacrifice some of the visual quality to maintain that frame rate. And so you're going to have to go in and do a lot of tweaks on some of these things like shading environment and whatnot. Okay, so I think that's going to cover it for my demonstration. This is pretty much what I did for GDC, and I hope you guys enjoyed it and learned a lot today on how to actually build VR content in Stingray. And last of all, we're going to go ahead and run the VR demo. And to do that, all we have to do here, because of our project.lua file, is go ahead and choose this Run Project button, and that will launch our VR content. We'll go ahead and save our level. Okay, so here we go. We've got our VR roller coaster ready to go. My Oculus headset is working. I can look around. Go ahead and hit the start button to get her going. Got a nice frame rate, running at VSync. Full 3D positional audio. Looks great. Alright guys, so I hope you enjoyed it, like I said, and I hope this helps you to build VR content in Stingray, and we really look forward to seeing what kind of stuff you guys come up with.